our next inviter talk by Piotr Dudek. So Piotr, if I'm pronouncing that correctly, which I never am, is a professor of the School of Electric and Electronic Engineering at Manchester University. He's one of the minds behind SCAMP5 processor, for plain sense processor that a lot of us have been seeing and using. So yeah, without further ado, if you're ready to present, please go ahead.
Yes, thank you very much. Thank you for inviting me to give this talk, and thank you to organizers for organizing this workshop. Very nice. Okay, yes. So title: On Sensor Computer Vision with Pixel Power Processor Arrays. I'll just kind of give a brief perspective and motivation on kind of my view on the principles of where, why we're trying to do in pixel computation, and then tell you a little bit about the chips that we designed in Manchester with a bit of an overview of SCAMP5. I'll show you something about a new chip, SCAMP7, and show a few applications and demos. There are other demos in this workshops. They are using SCAMP5 device, so I'll focus mostly on that. But just generally, and we kind of all notice that vision is hard, and the algorithms are demanding computationally, and so it's not just due to large amount of pixels, but one of the reasons certainly is the amount of data that we have to process. And since this is a robotics conference, robotic applications are extremely challenging, right? We often have to process things in real time with high throughput and low latency, especially if the robots are moving fast or have to react fast. If these are embedded systems that we want small footprints and low power consumption as well. So it's as hardware designers, we're really motivated by these robotic applications because they do present some of the most challenging application scenarios. So it's a demanding performance, but severely constrained size and power. And so you really cannot, send all the data to the cloud, which is a lot of computer vision, works like that. You cannot use even large or power-hungry CPUs or GPUs. You cannot even process data in batches. That often helps you to process fast. But you do have to maintain throughput and low latency. So huge challenges. And the conventional pipelines are really not efficient at doing vision. Energy is wasted right from the very start. On an image sensor, you'll perform A to D conversion. You run an image sensor pipeline, which does your demosaicing and gamma correction and sophisticated noise removal, and really with the purpose of producing lots of pretty pictures that you will send somewhere else. So that's already perhaps not necessary for vision. But then of course you have some sort of hardware that you try to throw at the problem to compute to get this data processed. And the key observation that I think has to be made, and is well appreciated by hardware designers, but maybe not for everybody, is that it's really not the kind of compute circuitry that takes power, it's moving data that takes power. So the power and speed is really limited because you have to move the data. Well, between the sensor and the processor, and then between maybe your processor and your co-processor, and within the system between the processor and the memory, or within your specialist hardware between your memory cells and your processing cells as well. So really, it's the movement of data that is limited. So what we're trying to do is to minimize that movement of data. And yeah, so that's what really costs time and energy. And the idea is, okay, well, we get rid of the conventional camera that sends pictures out and replace it with something smarter. We'll call it a vision sensor. And we'll try to squeeze all that processing into the sensor itself, which of course is very easy to do on a PowerPoint slide, a little bit harder when you actually have to build it. But that's our idea. So we'll put that processing hardware into the sensor and output meaningful data. And so we can then get away with something much simpler, a microcontroller. And that's really, I mean, this is the picture for that we all can understand in this workshop. But I think the movement of data, that is really kind of important thing. So bringing processing to data is why this works. And of course, I mean, what you do is basically integrate that processing circuitry onto the sensor device itself, and you can put it right next to the sensor, and that's a good solution. And of course, most of the kind of data movements are very local then, and we've seen already some solutions that doing this. Our approach is that we're trying to take it to an extreme and put the processing within the pixel array. So the idea is really we very closely integrating sensing and processing so that we don't have to pass data between the sensor and the processor. And also processors integrate memory. So everything is kind of very, very close together. Now, I want to give you this, which the scale here is transistors. It's a bit of a timeline, but it's not really a history lesson, but it's a kind of, it's what you can do with in-pixel circuitry. So, you know, when the image sensor started, there was a zero transistor circuit because CCD devices essentially just had electrodes that were biasing the substrate that was gathering electrons. And then these were sort of bucket brigade pushed out of the chip. Now, with the advent of the CMOS-based image sensors, people could do a more sophisticated readout circuitry with about 3 transistors. And most of the image sensors that you get are 3 transistor sensors called active pixel sensors. We are seeing now the opportunity of integrating more and more transistors into that pixel space, partly because we have the availability of stacking technologies, and partly because the transistors are getting smaller and smaller. And so this is an example of a digital pixel sensor from Facebook Labs. Sony have sensors like this as well, where the entire A to D conversion, which is one of the initial steps in the sensing pipeline, is integrated into the pixels, and that costs you maybe about 80 transistors per pixel, and you can put them right next to pixels. What we're trying to do is to put entire microprocessor into a pixel. Okay, we can call it computational pixel sensor or pixel processor array. At about maybe 200 transistors, we can already build very simple but effective microprocessors, and that's really that is our approach. And just a disclaimer: I'm not claiming that we are the first people who are doing this. I mean, with so much pleasure have seen the Professor Ishikawa's presentation. It's a seminal work that, similarly to Andy's, inspired me a lot when I started working in this area, and so it was very influential, and it continues to impress. And so that's the kind of there are people in academia who are trying to integrate the processors into pixels. There's a lot of other ideas that increased number of transistors in the pixel allows you to do useful things with time of flight sensors or single photon detectors, the photon counting sensors, with the dynamic vision sensors that we have seen in the previous presentation, and so on. So integrating more of the transistors into the pixel circuitry enables you to do more interesting things. And we are trying to do this in a very flexible way by putting a microprocessor into a pixel. So this is the general view, right? We will have this image sensor that responds not by sending out images, but sending out some information that it has extracted from the images themselves. And our approach is of integrating full processor into the pixel array. It's a challenge to do this. It's an interesting challenge, and you can see where the technology is going. We are capable of integrating more and more processing next to the pixels, and so we should exploit that opportunity. If you do this, then you can just write programs, right? So rather than having this sensor that does one particular thing, you can build a sensor that can do anything. That you can simply write one program to do some feature extractor, another program to do segmentation, another program to do key point extraction, and so on and so on. Challenge is how you're going to build your processor so that it fits into a pixel, and that's very much what we have been working on in Manchester, and that has gone on for a while, and so we've explored various ways of doing this. We've built a lot of work on the concept of analog processor that I will outline in a bit more detail here. And this latest devices, SCAM5 and the latest SCAM7, are really largely based on this idea of analog computation. But we've also looked at bit serial digital computation, similar to the work in Tokyo. We've looked at integration, kind of from a technology point of view, how you can split this processing amongst not even one but several silicon layers. So there's a whole family of pixel processor arrays that you can think about. But today I will tell you more about what I think is our best, the SCAMP5 sensor. This device is used in the community, and there are some demos in this workshop. Here we integrated 65,000 processors on a 256 pixel array. They are really slow if you think about a single processor, right? It's a 10 megahertz clock, but because there are so many of them, we are getting a pretty decent peak performance of sort of more than half a teraop, again at a power consumption of about a watt peak. The more important number is this ratio of how much performance you can get per watt. And without going into details what a gigaop means, because that's also rather contentious, these are pretty good numbers, especially if you consider that we are actually using a technology that was commercially available 20 years ago. I mean, you understand how processors get faster and faster as the transistors on silicon chips shrink. We're actually using a very, very old technology and achieve performance which is state of the art. Okay, now I usually skip this bit about analog processor, but I thought it's actually quite interesting, and why not tell you a little bit more about it? So if you look at this processor here, the analog is actually a large part of the system, but the way we design analog processors is quite special. We actually design an architecture of a digital microprocessor. So you can think about this analog computing as essentially being a way of implementing a data path. So the processor here, so if you kind of think about the schematic diagram, it has the registers, it has a data bus, it has some kind of instruction set and execute software programs. It's like any microarchitecture of a processor. What is unique is that the data path is analog. So the analog arithmetics are actually done by computing on analog values, in this case on currents. The registers are analog memories, and this we think gives quite high efficiency and a small circuit area. So that allows us to build a complete microprocessor with less than 200 transistors. Another nice feature of this is that you can seamlessly integrate the sensing with the processing. We don't need to convert data from analog to digital to process it, because the analog representation is the native representation for this processor. And I'll show you this, which is actually how the processor works. I'm not going to talk about the details of the transistors, but it consists of registers, which are memory cells. And really, like in any other microprocessor, what you do is you just run through the micro instructions, and each micro instruction sets up a path for data to be loaded from somewhere and stored somewhere else, and perhaps processed in between. So we can execute an instruction of moving a piece of data from a pixel to the register. We can execute an instruction of moving that data again from one register to another register. Or we can take data stored in two registers and put it somewhere else and add those two numbers together. So from the point of view of the architecture, this is really a processor microarchitecture. From a point of view of the data path implementation, data representation is not bit serial, it's not 8-bit, it's not 16-bit, it's an analog data path. Okay, so that computation is done in analog. But it just runs a program by setting up all these different paths for loading and storing the data in between. It's not the only way of designing pixel processor arrays. Yeah, we find this interesting, but most importantly, we find it effective. So resulting in a compact and low power implementation of this data path. And the program flow control is actually under a conventional sequencer, or in our case, we actually use an ARM Cortex M0 processor to run the sequence of instructions that will run on the processor. So if you look at the code, it looks quite familiar. It's basically C. We can compile the C into the instructions for the sequencer, and the analog operations, if you like, are encapsulated in processing kernels that you write essentially in assembler. And it means that the programmer does need to be, to some extent, aware that the computation is done in analog. Some of the peculiarities of this is that the computations are imprecise or noisy. but we do try to hide most of that complexity from the programmer, providing the libraries and tools that make the programming of the system very similar to that of programming a digital computer. So essentially just write program in C, write the programming kernels in assembler, compile the code. You have to understand, there is some kind of microarchitecture of that processor that executes the kernels, but to a large extent, you can forget this computation is done in analog. Although when you were looking at your computation results, you realize that there is a noise creeping out, and you may need to take that into account. We have spent quite considerable effort developing programming tools that allow the users to simulate the code and provide a debugging environment for developing applications, so we can actually simulate the whole system on a PC in a kind of emulated way and then run it on hardware. And that actually takes a lot of effort, and it's quite difficult to do in academic environments. So we've been quite lucky to have funding to do this sort of work. Okay, but that's in a way it's really essential that when you come up with this new and strange hardware architecture, that you do provide tools. Otherwise, no one can use your system, and you can write a couple papers about it, but that's just about it. Okay, SCAMP7 is our new chip. So I want to show you some examples, but just brief introduction to this new chip. It's quite similar actually, and almost backward compatible with SCAMP5. So there is not a great kind of technological leap here. We integrated some of the peripheral electronics that we had previously on a PCB onto the chip, just so that we can make a slightly smaller system. So actually, some of the biasing circuitry and all the periphery is now integrated somewhere there on the chip. We increased digital memory to 22 bits. So I talked to you about how analog compute is being used in the SCAMP system. It's actually a mixed mode processor. It has two parallel data paths. It has this analog data path for manipulating, if you like, a continuous valued information. It also has a binary data path for manipulating binary data. And a lot of people like using binary registers, partly because it's a little harder to compute with analog, and you have to think about the noise effects, and so we find it quite useful to increase the amount of digital memory there. We improve things like digital conditional write that allows us to do things like say in pixel A to deconversion faster. We increase readout speeds. So there are some kind of incremental improvements over what SCAMP5 was. And these systems are, we've tested them in the lab, and we are planning to make them available to our collaborators and the community in general, as we did with SCAMP5. I show you this one thing on analog compute again, because people often question this. I run here a median filter on SCAMP and just computing median filter from the input image in MATLAB, just so that kind of visually you can see what's the impact of this analog computation. If you look closely, you will see there's a little bit of noise creeping up here. So there is a level of imprecision or noise that is being introduced by analog compute. But if you think about what are we trying to achieve here, getting rid of this point noise, I mean both algorithms achieve that. So it's really a matter of adapting your expectations in terms of what is the goal here of the computation. Is it to have a perfect representation of what digital computation will achieve, or is it achieving a certain vision processing task? And if you think in that way, then you will find that this analog compute gives you an opportunity to do things fast and accurately enough for many applications. Here I'm showing an optic flow implemented on the chip, and it's simple block matching algorithm where we just see how a block of 5 moves from a frame to a frame. There is a color map so the color codes for the direction and velocity of motion. We can run this on chip at about 0.4 milliseconds latency, so it's about 2,000 frames per second if you wanted to run it in this way. But often that would be just a first step in some longer algorithm. Here I'm showing a corner detector. We're running a fast corner detector, so a simple corner detector algorithm. In this first, this first video shows how the corners are extracted and tracked with a gray level image background. What typically you would do is not to output the gray level images, but only output the corners, right? So you're interested in how your features move from a frame to a frame. You're not really interested anymore in gray level image behind it. And if you do this, then you can run this at something like 2000 frames per second. So we can retain maybe a few hundred coordinates of corners at 2000 frames per second. So you can do, and then you can follow that up with whatever you want to compute with those features. So there is some kind of address event interface which allows you to output not only like images, but actually coordinates of the points of interest. Somewhat similar to what DVS type of sensors are doing, the event cameras that output the coordinates of pixels that change intensity. But here we can, in a way, program what kind of event we will be sensitive to. So here the event is an existence of a corner point. With capability of doing things very fast, we can do interesting things in computing during integrating light. So typically, if you want to do a high dynamic rate sensing, you will acquire images at different integration times, and then some kind of algorithm that stacks them together and figures out what is the optimal exposure in different points. We implemented a tone mapping algorithm that works during integration. Essentially, as we are acquiring light, we're looking at the images and deciding whether the pixel, what gray level of a pixel should be depending on its neighborhood. This work has been done by one of the co-organizers, Julien Martel, and it's a very nice algorithm that allows you to capture images with high dynamic range. Another thing also done by Julien was depth from focus, where we were processing thousands of frames per second while sweeping the focus of a lens. So we had a liquid lens that was sweeping the focus at something like 60 hertz, going from near to far focus. And at that time, we were computing local sharpness in the image. And from that measure of local sharpness, when it peaks, the time at which it peaks can tell you about the depth of the image at that particular point. So you can get a really nice depth maps, which you can output at 60 frames per second, but you have to process at 7000 frames per second to get 128 levels of depth. This is the kind of implementation that you would never do with a conventional image sensor, because you would not be able to output, or you don't want to output 7000 frames per second from a sensor. But if you compute right on the sensor, you can start doing those things. I'll show you this one more thing, which is a target tracking. This runs at 100,000 frames per second. And what we say, we're looking at the spinning disk, and we're picking out a point at the spinning disk here, which is an O, as opposed to all the C's. And then we output the coordinates of that point. So we cannot actually output frames at 100,000 frames per second, but we can output the computation result, the coordinate of the point of interest at 100,000 frames per second. And this is the kind of time space that shows you like this. So this is the image space, and this is the time. And we show how on this rotating disk, the location of our point of interest of our O moves. We can output one frame just to make sure. So we output one frame out of all this kind of capture to show that our tracking really goes through the O. But we cannot output so many frames. So we can only occasionally output a gray level frame. Here is actually a video of this, of a slightly different scenario, where we are tracking all the points now. So the O is the red track, and the C's are the blue tracks. And we're returning one frame. All the other frames are processed, but only coordinates of the points of interest are returned. So that was a really nice demo, and showing potentially what you can do at extremely fast processing speeds if you can process on sensor. I have here the CNN demo. It's quite a complex algorithm, so we can implement quite complex things on the sensor. There is a demo. Laurie Bose has a demo in the poster session on this, so I'll skip this here. I'll show you some of the other things. Was again done at the University of Bristol by Laurie Bowes. Where what we are doing is essentially from the motion of the image on the image plane, we are determining how the camera is moving. So it's a kind of inward, kind of in-out looking odometry. The two tracks here is the one that is coming from a Vicon system that tracks the camera. So that's a ground truth, and the red and the darker one is the one determined by our system. So again, here one of these tracks is the ground truth, and the other one is determined by the system. The application context here, it shows how we compute a whole number of features on sensor. And rather than outputting the feature maps, we just summarize those features, calculating some summary information on a feature in a larger receptive field, so that we compress all this different information from feature extractors into a vector of 40 numbers. And this is the 40 numbers that we are sending out to the processor. And then we train a neural network to do. So here we trained it to essentially replicate the behavior of a behavior of a proximity sensor. Oh, my video is not working. So that the car is driving around and is avoiding obstacles. It was just the neural network that looks at those features was trained with just ultrasonic proximity sensors. So it's a kind of trying to mimic behavior of that using purely vision. Finally, here there are some videos that show our drone racing attempt. This is probably the most ambitious things we did with robots. So we put a sensor, the SCAMP system here on a flying drone, and the drone is flying through the gates. You can see what it sees. These are actually simulation results, but the idea is that from whatever the sensor sees, we will only extract the location and the position of the gates and use that info. So again, there's only a few bytes extracted per image frame, and only those have to be sent to the processor, and then we use that to control the drone. There is a few other demos in this workshop, so please have a look at other things that are being done with this sensor. This is just the summary of the talk. I will just quickly go to acknowledgements. There is a team in Manchester. A few key names are here. There were a few people over the years, students that worked on this, and our collaborators here that worked on the videos that I presented in this work. And that's all I have to say. Thank you very much.
Excellent. Thank you. Thank you for all of that. There's lots of really good information. We probably have time for a couple questions, so if anyone wants to put it in the chat, please go ahead. I'll start off by asking, what do you think? So you said that you're using a sort of 20-year-old technology for your process node. Do you think that moving to newer, smaller technologies is actually going to make the analog computation more noisy? And so sort of the latest, smallest technology actually would hurt in terms of accuracy and usability of the analog side of the device?
I mean, that's a valid point. The analog design gets harder as the transistors shrink, much harder than digital design shrinks in a pretty straightforward way. Analog is harder, but we definitely benefit from shrinking, from 180 nanometers to whatever 28 nanometers. People are designing comfortably analog circuits in 28 nanometers. So there is still a way to go in terms of scaling. But yes, the challenges are there. It's not as straightforward as scaling a digital 180 nanometer circuit into digital 28 and also there is a limit. I think it's hard to imagine the same principles that we used for designing this processor with the switched current cells working in 5 nanometers. So there is certainly a limit to this approach.
Cool, interesting. Yeah, so in that, how do you see sort of the going forwards the process of designing next generation SCAMP devices, in terms of you can always make things more fixed function or add more sort of special operations to do particular things, or you can make it more general purpose, almost to the point of like almost a CPU or something. Obviously you wouldn't go that far, but how do you go about deciding those things and working on where the compromises are to be made between what algorithms have to put up with in terms of weird or quirky novel instruction sets, and yeah, what computation is possible?
Yeah, so I mean, so there are 2 points here. One is special purpose circuits, right? So obviously, if you know exactly what kind of functionality you want to achieve, then you may want to use a dedicated circuit that solves your problem. And sometimes it can be a good solution. So in some cases, you know, like with, say, a DVS sensor, you are interested in capturing a lock intensity change beyond a certain threshold. If you know that's your function, you can try to implement optimized circuit for it. If you want to try to do more complex things, then actually this approach breaks down. For doing more complex things, you would need to build more complex and more complex circuits. And really, that is not efficient. It's a lot more efficient to build a small circuit that is universal, that in a way reuses the hardware because it multiplexes the operations in time. So, I mean, a microprocessor is a really nice machine that can solve any problem because it has a very limited set of hardware operands that can be reused and reused and reused again according to the sequence of instructions you give it. And so you don't have to build bigger and bigger system to solve more and more complex problems. You only need to give it a bit more time. So actually, that approach of fully programmable in-pixel circuitry is very efficient. Yeah? It's not just that, it's not a compromise, it's actually the way to build very efficient circuits. Now where things are going, I mean, there is a little implication now already with our move from SCAMP 5 and SCAMP 7 and adding a little bit more digital memory. As we are trying to exploit finer and finer technologies, that boundary between what is done in analog and what is done in digital will be shifting. And we will be doing more things in digital. We will still, I'm pretty sure we still want to do quite a lot in analog, because there is, at this very, very early stage of processing, it's really very efficient to compute without having to digitize the information, without running an A to D converter first. So at that very early stage, there is a place for analog computation. And then as things get more complicated, you can do things more digital. And I guess a hierarchical designs where you start with this pixel level computation that is good for many things, and maybe, as I think Andrew Davison indicates, is good for more things that a lot of people imagine it's good for, the pixel level compute. But there is also a place for parallel compute that is more flexible in the architecture, and that allows you to more flexibly communicate between the processors. So I guess for kind of practical systems, there will be a whole kind of on-sensor processing pipeline that will take you from analog compute at the sensory front end to digital compute near pixels to a digital compute somewhere which is still near a sensor array, but perhaps in a different topology or giving you more flexibility.
So
and it's, I think it's a big research question on how that pipeline actually should be constructed.
We're running low on time. One more question, and if you can answer it in 2 or 3 words, what would you think is the most compelling demo or coolest next thing to show off with these capabilities?
I don't know.
Excellent. Well, thank you very much for your really interesting talk. Thank you for coming.